A long time ago, girl.
A very long time ago, huh?
Uh-huh.
Okay, then there comes Dr. Terrell.
Here I am. Where are you? Ugh.
Dr. T, why does number 2 have like 30 questions by itself?
I don't know. I don't know who wrote that. He was a crazy man.
Do you know him?
Nah. He's a crazy bastard.
Wow.
Like, it's like a 30-part question.
Yeah. I know. It's written by a pure sadist. Someone who hates you personally.
Was this before or after the gin and tonic? Because this seems like a before gin and tonic type of questions.
These are pre-gin and tonic. These are days when the author didn't even drink. Can you believe that? He was too snooty to even get loaded on suitable nights. Let's see. So, think about these questions though. Like, why is cold denaturation required? Well, that's a fair question. That might require a couple sentences, But what is the IR wavelength used and why? Well, it's just going to be like, 1,000 or 1,500 nanometers because that's where water absorbs, What's the IR pulse width? 9 nanoseconds. What's the IR heating rate? 3 billion Kelvin or 30 billion Kelvin per second, What's the temperature change? Plus 30. What's meant by term counterpropagating beams? Well, they propagate in opposite directions. What is a transient grading? Why might this be bad? Well, grading is a periodic distribution of intense and weak signals, and that would be bad because it would make a thermal grading, and we want uniform heating. What was done to eliminate the possibility of a transient grading? The counterpropagating beams. What's the IR beam diameter? 2 millimeters. What's the UV beam diameter? 200 microns. Why are they different? Well, because you want the UV beam in range of the IR beams, because you want it to sample only the heated part, only the uniformly heated part. What's meant by steady state? Well, we're going to answer all these questions, aren't we? Even though they were written by a sadistic maniac. 2.6.9. Oh my God, no. Geez, this is crazy. Okay, so who wants to answer all these questions? Nobody?
Dr. Terrell does.
Dr. Terrell does. Yes, he does. But he wants to know if any of his students want to answer them. Do any of his students want to answer these questions? Please? Okay, I'm not going to answer them. We'll go move on to a new paper then.
What question do you want us to answer, Dr. Terrell?
No. I'm just joking around. So part one is just my synopsis of what this is, right? So let's answer question 2.1. This is going to be a bit of a challenge for those of you who don't have two devices, but beware that we do have the video is being recorded for these guys, right? So I'll make some notes and you guys can paraphrase them, right? Who wants to answer for me why cold denaturation is required? We already answered this last time. Super easy.
It's easy to
Oh, I love it. He sounds like Max Headroom on Max Headroom. So Richard, can you guys hear me okay?
We
Yeah.
can hear you okay, Dr. Terrell, but
Okay.
Richard was a robot, yes.
Yeah, Richard was roboted out. So
Sorry.
that's all right. I'm actually gonna put in my headset because I think the audio is a little bit better. Eh. Why did I get rid of my stupid grass background? I'm in my office now. You know, hello, Carla. Hello, Aditya. Yo, Adam. Chilling out. I can see the top of Adam's head. So, um, first time we played the shame game, then we played the blame game. Oh, hey, Kenya. Oh, you're like on a beach in Yucatan. I love it. And Calvin,
Did you just
yet again. Ah, Ivy. How's it going? Kai. Woohoo. Dan. All right. So, who should I pick on? Ivy.
Yes, hello.
Why is cold denaturation required for this experiment?
Because it's easier to heat or to, what was it? To heat something up quickly than cool it down quickly?
This will be the name game. Did you say something, Nancy or Ivy? Sorry.
I didn't realize that. It's
I can't hear anything Ivy's saying. Maybe I messed up my own audio. Can you guys hear me?
It's saying that he keeps muting me.
You guys can hear. I can't hear anything.
Hello?
What the hell is going on here?
Can y'all hear me?
Turn it.
I can hear you, Ivy.
I can hear you.
Hello, Dr. Terrell, can you hear me?
I can hear you now.
Okay, cool.
Yay.
I said it's because it's easier
Sorry.
to heat something up quickly rather
You want
than.
to say why cold denaturation?
All right, I don't know if you can still hear.
She was giving you the
I can
answer.
hear you. Yeah.
Damn it. My stupid thing goes away.
Dr. Terrell is like Internet Explorer.
Okay. Can you guys hear me?
Yes.
Okay.
Hello?
Hi, Ivy.
Is it working now?
Yes. I threw
Okay.
my headset away.
I'm gonna try this the fourth time.
Thank you.
It's actually might have it backwards. It's easy. I know that we'd say that it's easier to heat something up rapidly rather than cool it down rapidly. But now thinking about it, I might have it backwards.
Okay, all right. Hold on. So, do you believe in cold rays?
In what?
Cold rays.
Cold rays.
Cold rays. Yeah, there's light rays,
Okay.
and then there ought to be dark rays, right? And the carrier of the dark ray is the darkon. There's the photon and the darkon.
Ivy, I think he's messing with you.
You think I'm messing with you, Ivy?
I wouldn't be surprised.
Good. Excellent. So, but the point is, right? How do you cool something? You get everything to spontaneously just spit out a bunch of microwave radiation? You can.
Oh,
You slow it down technically? I don't know.
Well, you need a bunch of nano-kais in there that are going to grab all the atoms and try to absorb their kinetic energy. And then what do? Now you're hot because you have all their kinetic energy.
I pass it on to something else.
Yeah, but then that's hot. You have to radiate it, right? You need a bunch of kais with a bunch of nano antennas, and and all at the same nanosecond, you grab a molecule and you decrease its rotational and vibrational quantum numbers instantly, converting that energy into microwave and near infrared photons and squirt it out of there. But that just doesn't happen. I mean, maybe I haven't seen Batman enough. You guys know what I'm talking about? Okay, there's 2 points for anybody who knows what my Batman reference is.
can you repeat the reference again?
2 points to who I'm talking about when I'm talking about cooling stuff.
Dr. Freeze?
Close. Mr.
Mr.
Freeze.
Freeze.
Dr. Freeze.
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 Mr. Freeze. I'm going to give it to Kai. Excellent. Kai's on the board. 1 point for Batman. Ivy gets 1 point because she got it right, even though she choked when I started messing with her mind about whether it's possible to cool something quickly.
In my defense, I just muted myself. I did not choke physically.
I know you didn't choke physically. I'm not trying to kill you guys, just mentally.
I don't know. Seeing how many questions are on this document,
I
I'm
know.
baffled.
I know. But this is like way, way, way easier than the midterm. Trust me, Dan. These are like one-word answers. They're not, I mean, someone who will go unmentioned complained about me assigning another goddamn take-home midterm thing. But the thing is that this person puts a lot of effort into the answers, and I love it, but I'm not really looking for that much because I am lazy. And like, if I see that the basic info is there, I give it all the points, right? And then this person who will go unnamed is constantly making these grand soliloquies and saying like, Nobel Prize answers, and I can't give him more points because I'm too lazy. So anyway, this is for the lazy people. This guy here. So why is cold denaturation required? Because it's easy to heat in 1 nanosecond, but impossible to cool in 1 nanosecond. Right? What do you think, Calvin? Yeah? You give it to me this time? Maybe?
Yeah.
Okay. Gosh. I feel like Rodney Dangerfield. Who knows who Rodney Dangerfield is? Oh my God, I have to give points for Rodney the freaking Dangerfield? Come on, Richard, you know who he is.
Yeah,
A comedian.
Okay. Calvin said, is that a comedian? That's worth a half a point. Who is Rodney Dangerfield?
Pro wrestler.
No. He sounds
Before
like
our time.
he's before your time, but he just died.
He's like a
What is
movie
he?
star, right? Something like that.
Yeah.
Isn't he cowboy or something?
No,
Oh, come on.
he's a comedian. He was on Johnny Carson.
I thought, yeah, so I thought he
Good.
was a comedian. So isn't Calvin right?
Alvin's right. He gets a point. But somebody has to know. His tagline is, I'll get no respect. I'll get no respect.
I know that from The Office, not from him.
Right. So one of his funny jokes, which was went out with my wife, with my fiance for 5 years. She said, no, I'm good Christian. We have to wait to have sex. And now I'm married. She says the same thing. That's stupid. Shut up, Roger. God. Okay. Calvin.
Yes. Oh,
Calvin gets 1. Okay. Okay, so how do you heat something in 1 nanosecond?
Lasers.
Laser, exactly. A laser pulse. Tuned to what wavelength? In this case, since it's an aqueous sample. Or tuned to the frequency of absorption of
1500 nanometers?
no.
No.
100 nanometers is vacuum ultraviolet. Sorry? It's actually 1500.
I said 1500.
Oh, you said 1500? I'm sorry, I heard 100. My bad. Okay, so I get to give you a point now in the name game. Okay, so Kai's up to 2 because he got Mr. Freeze.
Do I get a point for lasers?
Okay. Carly gets a point. All right. So, and you tune the laser pulse to 1500 nanometers, right? And, okay, so actually that's the answer to the next question. What is the IR wavelength used and why? So let me, let's go to the paper here. And that's discussion experimental. Okay, so it starts up here. Heating and sample cell. Who wants to read this for me? Calvin.
where?
Starting at heating and sample cell.
Till okay. The sample. Can you guys hear me?
Yes.
Okay. The sample is held in a custom 0.4 millimeter path and fused silica cell, cooled by 2 thermoelectric devices. The temperature is held constant to less than 0.2 degrees Celsius by a thermistor. Feedback loop. 2 it is less than equal 120 it is millijoules, and then 1.54 micro. This is micro. Yeah. Micro infrared beams are generated by Raman shifting. Is it A7 millijoules, neodymium, yttrium, aluminum, garnet laser in a mode optimized high efficiency methane cell, resulting in uniform near Gaussian heating profiles of 2 millimeter diameter. The counter propagating beams are delayed by 8 nanoseconds from 1
Okay, stop.
Okay.
So let's stop at 2 millimeter diameter here. Let's see. Sorry, I probably should have done this earlier, but the sample is 0.4 millimeters, right? So it's less than a half millimeter thick. And it's infused silica, cooled by 2 TE coolers. In a thermistor feedback loop, right? So here's the important bit. 220 millijoule, 1.54 micron IR beams. Hold on, let's, I'm blanking on something here. Let us go to the literature and say ND YAG wavelengths. (1064), right? 1064 is the main wavelength of the yttrium aluminum garnet of the YAG laser, the neodymium doped YAG. There's also transitions near 946, 1120, 1320, and 1440. Let's say we're using the 1064 line. And what is done is Raman shifting. Okay? And they don't say it, but they mean Stokes Raman. So 1064 is Stokes shifted to 1540. Yes. It could be 1440, 1320, or 1120, or 946 is Stokes shifted, but I'm almost certain it's 1064. Okay? So 1064 is Stokes shifted to 1540 using using what chemical here? Dun, 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 dun.
Are you referring to this neodymium yttrium aluminum garnet thing or no?
That's the laser, right? It's neodymium, I think, is the active, it is the chromophore, right? And yttrium aluminum garnet is the matrix in which the chromophore lives. And the neodymium output is at 1064 nanometers, 1.064 microns. And they Raman shift that to 1.54 microns. So it's 1.06 to 1.54. So how does that work, guys? What is taking the energy away from the photons?
The methane cell?
Methane, right. Richard is on the board.
Sweet.
Richard is on the board with 1. So now, can Richard follow that up by telling me what specifically about the methane is shifting the wavelengths?
The hydroxyl group on there. I'm
Okay,
sorry.
you just
That's
lost
totally
your
wrong.
point.
Yeah.
You just lost your point.
Yeah.
Methane has a hydroxyl?
No, not at all. I was thinking methanol.
Yes, you were. Aditya, what's the chemical structure of methane?
Is it like 4CH something?
No!
CH4, I want my phone back.
It's CH4. Oh,
That's
Oh
what I
my
said.
you said 4CH. Ah!
You're mistaken.
Aditya, this is recorded.
My internet
Nobody's
connection
gonna
is
listen
bad.
to it. Trust me, nobody's gonna listen to it.
We will to do the homework assignment.
That's possible, actually. That's possible. Okay, so so methane. Now, what quantum interaction does methane have with the yttrium aluminum garnet radiation that it can shift its wavelength? I mean, it's a Raman, right? It's a Raman shift,
Scatter.
right? It's scattered. And where does the energy go from the laser beam, from the laser photons? Happens photon by photon. There's a 1064 1.06 micron photon that's shifted to 1.5 micron photon. Oh, come on, guys. Oh my gosh, I'm gonna have to go back to the midterm and take points off.
Stokes shift?
Yes, it's a Stokes shift, but where does the energy go? Where does the photon energy go?
Oh, is it like with the holes and stuff? No.
No, that's a semiconductor. That's more like an electronic transition. In that case, you would say that the energy went into the creation of an electron hole pair, but not in Raman.
Like the fluorescence and emission thing, doesn't that like affect energy?
That's much closer.
Can you repeat the question, please?
Yes. Where does the energy from the 1064 nanometer photons go when those 1064 nanometer photons are converted into 1560 nanometer photons?
Does it have to do with the bonds in the methane?
Yep.
The vibrational mode.
Who said that? Who said that?
Ivy, me.
Ivy! I can't see you, but you are correct. Ivy gets on the board with 2 points.
She's a,
I was already on the board. I'm in the first line.
Oh, sorry. You get 2 more points because you said it was easier to heat faster than to cool. Exactly. I like it. Pulls ahead of Kai, who got my Batman reference to Mr. Freeze. Alvin, Carla, Richard are tied for 1, and Aditya, who had 1 but lost it when he said 4CH. Close, but no cigar. Okay, so you can take a laser pulse and detune it using a gas cell. And you basically just fill a long cell full of high pressure gas. And hydrogen is often used, H2, because H2 has a fairly high energy stretch, right? And CH4 has a lower energy stretch. But CH4 has a perfect energy stretch to tune this 1064 into 1540. 1540 is right on 1540 nanometers. Oops, 1540 nanometers is right on the blank of water.
Borderline?
Yes, sort of, but $15.40 is right. $15.40 is, it has something to do with water, right? What is 1540 nanometers to water? If you're liquid water and you see a 1540 nanometer wave photon going by, what happens? Adam.
Does it absorb?
Yes. Absorption.
Yay.
It's right on the absorption band of water. Okay, good. So, good. But you don't get points for that because you just said absorption. And I had to prompt you. Get a half a point.
I'm okay with this.
0.5. Okay, so how do you turn a YAG into a water heater? Calvin?
Can you repeat your question?
How do you turn a YAG laser into a water heater? Oh my God. Who can answer that? Richard? You're smiling smugly. Ah, now you disappeared.
You can basically stoke shift the laser beam by going to the methanol, the methane cell, and that's right at the absorption of water. And
Exactly. But you said methanol again, meaning methane. That's all right. I'm going to give you another point and a half. Half a point docked for saying methanol again. So, Ivy.
Yes, Dr. Terrell.
How do you turn a YAG into a water heater?
I know Richard just said it. You put what are words?
What are words?
You put the YAG laser through the methane cell, which will stoke shift it to exactly the wavelength that is on the absorption band.
Exactly. And what process is that, Aditya?
I'm sorry? What do you
What process stoke shifts the laser beam?
Oh, the methane
Yes.
vibrational modes will
Yes.
capture some of the energy from the laser and then stoke shift it to 1540.
Through what mechanism?
What?
Through.
Raman scattering.
Oh,
Oh, she stole it. She stole it. She stole it from Aditya. I intentionally was talking to Aditya because I'm being racist and Aditya is Indian, I think. And she stole it. Ah, don't let that happen again, Aditya. Be proud. Okay.
I'm sorry.
Dan. What? Oh, God. Please don't anybody watch this. I'm going to be in so much trouble.
This is recorded, Dr. Terrell.
Somebody erase it. Okay. So, what's next here? Okay.
Is
So,
anyone else hearing that feedback? on the
Yes.
microphone?
Kind of staticky.
Yeah. Dr.
Yeah.
Ted, you might have to reset your
okay, all right.
audio.
I'm going to reset it.
I think it worked last time. You just turned off your mic and back on.
Yeah, I'm trying.
It seems to be gone now, yeah.
Yes.
Isn't absorbance a log function? Oh,
Exponential.
Richard also wrote it in the chat.
I also meant an inverse square exponential. Because it's a square, isn't it? It varies with the square. Really? Okay.
Could you repeat that again, please?
Isn't it most intense at the shortest distance? Yeah, so it's true. Yeah, yeah, so yeah, I agree with Richard. Oh, me? Oh, so since the light is most intense when the distance is shortest. I think you're talking about the power? No, wait. Yeah, so it heats up the fastest at the beginning.
And the one closer to the eye.
No. Well, something that just resembles that first part that you kind of highlighted.
Shouldn't it look like that? Sorry. Yeah, like that.
Like C.
Like C almost, but maybe with a
Yeah.
little curve. D. No, it was can because um You want it to decrease. That's it.
Is it because it's like constant?
So it's like a more gradual decrease rather than like super fast.
Yes, I'm actually right next door to you, Dr. T.
8. Guessing.
10.
Oh wait, oh you actually
Is it 10? Okay, it's 10.
It's 10. It's 10. It's 10. It's 10. It's 10. Yeah, it's 10.
Because
yes.
Is that the same as counter propagating beams?
I've had a headache since 7 a.m. So thank you.
Circular dichroism. Oh.
Fluorescence. Me. You called on me, so I said it.
We cannot see your screen.
On the whiteboard.
feet.
2 feet?
Would it be Kelvin?
Kelvin per second.
Per second?
It's like 5 times 10 to the 9. Carla. Increase of 30 degrees Celsius. Like you have two beams and then one of them goes in one direction and the other one goes in the other direction.
It's like the same line, but opposite directions. Perfect. Okay, figure this one out. Okay. Okay, what is a transient grating and why would it be bad? Well, a grating is an interference pattern. And it would create hot and cool spots. In the water. That would be bad for kinetics, right? The phenomenon will broaden. Okay, what was done? What's the word we use? Counter what?
Propagating beams.
Exactly, and that was Carla, right? Right? Well, that's not a question. Okay, what is the IR beam diameter when it hits the cell? Who knows that one?
Was it 2 or 4 nanometer?
Nanometers? What?
I mean,
No.
millimeter.
Microns.
Okay, we've got nanometers, millimeters, and microns, but how many?
4.
For what?
200.
What? 400?
I said 200, but I don't know if I was right.
No, that 200 microns is the UV beam diameter.
Right. Actually, I think the 2 millimeter beam diameter, right? Nobody got points there.
You beat
Had
me
hands.
to it. I was about to say it.
You were about to say it. Oh no. Oh my gosh, I stole it from you. Okay. What is the UV beam diameter?
200 micron.
200 microns, Kenya, right?
Can I get a point for that?
That's my name.
No, because Kenya said it. I did not hear your voice.
I said it when we were talking about the IR beam.
Who just said it now?
Me, I said it.
Okay. Okay. Alrighty. Who did I miss for the 2 millimeters?
Me,
Who is me?
person
can't
next door to you.
Oh, Pauline. Great. Excellent. Pauline gets a point. Excellent. Okay. So why are these two regions different? You could say why. Yes.
Oh,
Mhm. Go ahead.
because you want the UV beam in range of the IR beam to sample uniformly heated parts.
Perfect. Perfectly answered. Kenya's pulling ahead here.
Anya gets 5 points.
2 points. So good. So why are they different? Okay, because the UV beam should sample a uniform temperature, or let's say uniformly heated sample, right?
We can't see what you're typing.
Okay, I'm on the wrong thing here, right? This is where I'm supposed to be, right? Because, yeesh, what a sucker here. Hold on. So, okay. Okay. So now, moving on here. So we've moved on from this guy here. Now what we're going to talk about here is I know we only have a couple minutes, but might as well take advantage of them. Here's figure 2. And these are described as steady state. Oh, darn it. Figure 2A is described as steady state. And so what is meant here is that each of these CD spectra are taken, over the course of a minute or so to determine the ellipticity factor for the protein to get an idea of its folding state, right? And the fact that they're steady state, what is meant by that is that they are nearly at equilibrium. That there's that the temperature is constant and this samples are not changing significantly during the time frame of the experiment. So I would say equilibrium might be a better term, but steady state is not correct, because steady state implies a constant change. All right. Enough for today? I can't hear anybody, so I assume that I've been like offline.
Dr. P, when is this due?
I don't know. Maybe this will be our last paper. I don't know. I've been thinking of something fun to do for the last week or so, right? But just work on this. Maybe we'll make it due next Thursday.
Next Thursday is
I think that's Thanksgiving.
Oh, okay. Perfect. Thanksgiving night then. No, I'm just kidding. I don't know. Maybe the following Monday night or something. Okay, I'll figure it out. I promise. I'll notify everybody. I'll be nice. I promise. I'm giving you too much time anyway. Is that a microphone, Calvin?
It's my massager.
Oh, I love it. I love it. But because you have your background on, it sort of disappears partially. It looks like a microphone. Alrighty, guys. Thank you so much. I will see everybody next time.
Bye, Dr. T.
Yeah.
Bye, Dr. T.
Thank you.